Hello, everyone, and welcome to our show. My name is Elftheria, and today I have the pleasure to have with me Austin with a new amazing project and something that we definitely haven't seen before in Volvox. If you're new here, Volvox is a community, but also a software development company. We are right now on the community side of things, and we like discussing with our community members. Hi, Austin. How are you?
I'm doing great today.
Perfect. Can you please share a little bit about your background so people can get to know you?
Yes, I am a hobbyist coder. I generally do my own research. I've been learning programming since I was 14, so I've been practicing for 20 years now. Back in the day, I first learned Liberty Basic was my first book. I picked it up from the library at my high school, read it, didn't fully understand it, but learned a lot of the basic building blocks for proceeding into where the point at which I received my calculator. And this was in 11th grade. I was a junior in high school. And the calculator obviously has programming language on it. And I used that to learn more programming concepts. And I was able to further my knowledge based on that. And then later I started learning Python, and now I've taken and mixed the two together in order to create this neural network.
Okay, that's amazing. So I know that you are doing pattern recognition capabilities and you're doing all this in a calculator. Would you like to share a little bit more about that? And also, if you could share with us the calculator, it would be amazing.
Absolutely. So the project started because I had a thought, it just crossed my mind. What if? It wasn't a I will, it was simply what if? What if I put a neural network on a calculator? Is that possible? And I said, if it isn't, that's okay. Because if I find out that it isn't possible for me, then I can just walk away and say, well, that wasn't possible due to the constraints. But people told me that it was impossible. And I said, I'm not so sure. And thusly, I decided that I would try. And when I began trying, I started seeing some possibilities, such as I began by trying to run the neural network on the calculator itself, which is a big mistake because there were variable overflows, and these are unavoidable due to the floating point limitations. It only goes up to 5 decimal points. But when you try to do so many matrix multiplications, the variables begin to explode and you can't stop it. Normally it would clip, but the variables become so large that they exceed the ability of the calculator to process them.
Okay, would you also like to share this calculator and demo it for us, please?
Absolutely. Let's give it a shot. So I will pull open the calculator, and I have here we go, the Hermes Optimus home screen. If I hit enter, it should open, and there is an about section, mentions the architecture, and there's the classify section, which is where you run inference. And now I will type in an incorrectly spelled word.
Okay.
Let's try BOCK instead of BACK and see what it does. All right. And as we pull up this here and hit enter, it'll take about 10 seconds because it's a 15 megahertz CPU. And it should be almost halfway done. You should see, there we go. Now just give it a few more seconds.
Yeah.
And there we are. It has the input, the result, and the confidence score that it had when it decided on the word.
That's very impressive.
Oh, thank you so much. And I will give some more examples without running them on the calculator because it takes quite a while to process. Glacial in comparison to the inference that we run today. So the original version of the neural network had only 4 input neurons, 60 hidden layer neurons, and 12 output neurons. As I decided finally to upgrade to version 2, I decided that there were some inconsistencies. Prior to this, version 1 was unable to correct BOCK to BACK because it did not have the letters, it wasn't able to differentiate enough between the letters. because I encoded the input letters as normalized, which means that they are divided by into, so they are encoded by dividing each number by its position in the alphabet. So A is 1 divided by 26, and Z is 26 divided by 26. When you do this, this creates sort of positional awareness in the calculator that I did not realize when I started the project. Relativity of the letters numerically creates a sort of association. So instead of typing the word, let's see, dark is a good one to test on. There's 12 in the original and 24 now. So dark is one of the originals. If you typed in CBQ and the letter L, so CBQL, each of those letters are alphabetically adjacent to the letters in the word dark. And if you were to type that in, it would correctly assume that the word you were trying to type is dark. And that is because the network learned that those letters were close to one another due to how the letters were encoded. Initially, it had the 12 output neurons, and those output neurons were associated with one word each. But in version 2 and 3, I have changed the input neurons. In version 2, the input neurons are 30 input neurons. And this is because I have encoded the letters not only relative to one another, but as a bag of characters, which means that it tells the calculator which characters you have specifically typed in, and not simply how close they are to, and that is the input layer. In version 2 and 3, the hidden layer changed to 50 neurons because of the larger input layer in order to fit it within the calculator's RAM. And the output layer changed between version 2 and 3 from the 12 singular output neurons to and it would output 0 or 1 for each of the 12. The 12-bit, the 24-word dictionary uses 12-bit encoding with a binary code book. Each of the 12 words is assigned a unique 12-bit binary pattern based on its index between 0 and 23, 0 being it is 0 indexed. So the 24th output would be 23. And the network outputs 12 sigmoid values, which are thresholded at 0.5. And this gives a 12-bit binary vector. So this vector is compared against the 24 predefined patterns using what's called Hamming difference, which is counting differing bits. So it says each output bit, count how many there are. And it says it differentiates via the pattern in the code. And the word with the closest pattern wins. So the output neurons, there are 12 bits specifically because 12 bits gives you 2 to the 12th power possibilities, which is 4,096. So these 24 words fit easily within this. However, you cannot train it on much more than 24 words due to the limitations of the hidden layer, and there's no room left on the calculator to increase the hidden layer. I'm currently at 869 bytes, I believe, left on the calculator, which is a very tight, very close to the limit.
You've already mentioned some of the challenges, but what other challenges did you encounter in this project?
Yes. So we can go back to the challenges. We've talked about rather the limitations of how much RAM I have left, the limitation of training on the calculator and the floating point integers. And that when you try to train on the calculator as well, 25 to 50 epochs takes perhaps 2 hours. And once I trained on the PC using the Python scripts to output the weights and biases, I ended up needing an exceedingly large number of epochs to train this neural network, because I do believe the size of the hidden layer creates a sort of bottleneck for the epochs. And perhaps bottleneck isn't the greatest analogy or word for it, but it inflates, I think, the number of epochs you need. I haven't exactly pinned it down. I've talked to some other people, and they seem confused about it as well. But when I trained on PC, this took 500, and 25 to 50 took 2 hours on the calculator. So this limitation is what led me to training in Python on the computer and exporting these weights for the calculator. And it would take approximately 2 years to train on the calculator at that, number of epochs.
Yeah.
So I quickly decided that the integer overflow and the length of time was pushing me toward finding another solution. And after that, I tried outputting the weights and biases as matrix and variable assignments and list assignments. This inflated the program size so large that it wouldn't fit on the calculator. And that is where I decided to convert the matrices and lists to CSVs. And these CSVs can be converted to the specific matrices and lists that the calculator accepts. These variables are specifically designed around the calculator's hardware. And once I trained on PC, I finally got the weights and biases loaded, and I ran inference a few times, and I ran into many errors, and then I finally stopped running into errors, and it ran inference. And when I finally typed in an incorrectly spelled word, it got it right the first time, and I was so surprised. I was like, oh, yes, it's possible. But the moment when I ran inference, I said, well, how far away can we go? It got just a scrambled word, right? What happens if I type in letters that aren't even in the word? And then it started correcting those. And I was like, wow, okay. So this is a lot more sophisticated than I initially thought that it would be. Some of the other hurdles included the RAM size, which I've kind of covered already. There's only 24 kilobytes. Every piece, every part serves a purpose, and no part is extraneous. And I think that is part of the thing that holds us back, is that we think bigger is always better, that the limitations are too great, that the constraints are creating a barrier. But to me, sometimes constraints breed creativity. They force you to look at things from a different perspective.
As we are coming to the end of this conversation, is there anything else that you would like to add?
Let's see.
For how long have you been working on this project?
Been working on it since May of 2025. And I finally got it to run inference in June. And as soon as I did, I hurriedly put it up on a website so that I could share the research that I had done with others. And hopefully, whatever I discovered will help others discover something to create technology that is affordable. Smaller devices can run things that we didn't think that they could. So if we can do that, we can create devices that are affordable, that are smart, that can do things for us. Perhaps you could take the same technology as a PDA from the 90s or the early 2000s, and you could use that same exact hardware today, and it wouldn't be difficult to produce. And perhaps you could just have an email assistant on there, and you just say, all right, so schedule me this interview at this time, and set a reminder and send an email out. And you could possibly run it on something that is not hundreds of dollars or thousands of dollars expensive phone. You can just have a little PDA, you buy it at a cheap price, and it functions and it serves you in a way to further your time management and the amount of time you have to work on other things.
Perfect. Thank you so much. That was actually a lovely conclusion. And for me, this was also a very unique project and something that I hadn't seen before. So thank you very much for presenting it to us. I will leave in the description box a link so people that are watching us right now can also check this project on their own. And if you have any questions for the folks that are watching us right now, do comment below and we will do our best to answer them. Thank you very much, Austin, for being here with us today.
You're welcome. The pleasure was all mine.